Let's start with the grid computing part of our course. This lecture is our first introduction to grid computing, and we will give you an overview of grid technology as a transition from cluster computing together with the motivation and benefits of grid concepts. You will also get a first grasp of the grid architecture and the different components that will make up a grid system. Finally, we will wrap up with conclusions and best practices and whether or not to use the grid for your particular application. Grid computing is a dynamic and loose federation of resources and institutions that enables researchers to solve large computational problems and store large amounts of data. The resources are geographically distributed and heterogeneously interconnected with fast network connections. The grid can be thought of as a cluster of clusters. It consists of various clusters which are distributed across the world, sharing compute power and storage capacity over the internet. A grid user is able to use all of this computing power simultaneously in a transparent way, without having to log in at all the different sites. The grid middleware takes care of the job distribution among the resources by providing an abstraction layer on top of the different clusters and the software that is running on them. So resources and users belong to virtual organizations to apply collaborative science in practice. Let's take a look at what happens when you are using multiple clusters at the same time. So what you can see is that we have 4 clusters which all look the same, and people start distributing jobs across the different clusters that are available to them. So you can immediately see that the cluster on the far right hand side is underutilized, while the queue is growing on the third cluster over here. And this is one of the problems that the grid middleware tries to solve. You can of course distribute jobs across multiple clusters if you do it yourself, which involves a lot of manual labor. But it's probably easier to have some central system do this for you. This is what we call the WMS, or the Workload Management System, and that's what we'll show in an animation to come. So let's talk a bit about cluster versus grid computing. What you see with cluster computing is that it's usually just one site, which has the benefit that you, for example, have local storage with a shared home account. And the scheduling software, so the stuff that we've seen before with PBS, allows you to save your data directly back into your home directory. When you look at the grid, which has multiple sites, no such facilities are available. So you have to distribute your data with your jobs and send the output that you have created to another storage node to be able to retrieve it. On clusters, you can just authenticate with your username and be on your way, while on grid you need both the username to access, for example, user interface, but also a grid certificate to be able to use the different resources on the grid. With clusters, there's a relatively homogeneous hardware set that you can look up easily what all the hardware is about, while with the grid, with all the distributed resources and little knowledge on where your application will actually run, the hardware is very heterogeneous. So you have to cope with that in the way that you create your jobs and schedule all that software. With clusters, you can directly submit your job to a particular cluster, while for the grid you have to do that through the grid middleware. And finally, and this is a major point and a pain point for many people that are trying out grid the first time, is that there's on grid a lack of local software. So where on a cluster you can either put software in your home directory or ask a system administrator to install everything for you, with the grid you will need to supply this software yourself. So this is something to take care of when creating grid jobs and scheduling your software, that you have to be able to send all of that software with your job to be able to run your own application. So let's briefly take a look at the motivation for this kind of infrastructure. So during the last decade, grid has gained worldwide recognition in the field of high performance and distributed computing. The grid aims to secure sharing of geographically distributed computational and storage resources among organizations, either public or private, who own these resources. Due to sharing and co-allocation of the infrastructure, the trust and strict security mechanisms are inherited in the grid architecture by design. The availability of such huge capacity of computing and storage can be of benefit for various researchers worldwide. This explains why grid computing has its origin in academic research. An example of novel research is the Large Hadron Collider. The LHC is currently the world's largest and most powerful particle accelerator. The ALICE, ATLAS, CMS and LHCb experiments generate enormous amounts of data that are impossible to be processed on a single site. So for this reason, 150 sites were put together, offering approximately 250,000 CPU cores, 160 petabytes of storage and about 90 petabytes of tape storage for the simulation, processing and analysis of the LHC data. Later on in the course we'll have a use case explaining what they actually did. One of the great benefits for grid computing is the transparency, so the ability to use different resources spread across the world with this one grid certificate that you have. And the grid middleware hides much of the complexity of this environment from the user, giving the impression that all of these resources are available in a coherent and virtual computer center. Another advantage of grid computing is the single sign-on. Users authenticate themselves only once and then have access to multiple grid resources without the need to log in to each different site separately. Trust to the various sites is established with digital certificate authentication. This implies that grid provides a safe environment for collaboration. Details of this mechanism will be given later in the course. In addition, grid computing is highly efficient as resources will seldom be underutilized. The middleware, which acts on top of the scheduling system such as PBS, coordinates this collection of interconnected clusters and in combination with large numbers of users ensures that these resources are used efficiently. The notion of a computing grid allows users to take advantage of parallel processing, making compute-intensive applications feasible. An existing application that is not possible to run on local resources can be submitted to the grid and run remotely on different machines. Okay, to give a first overview, we'll see how the different building blocks of the grid fit together. So we of course start with the user interface and a user, and the user connects to the grid by using this so-called UI, the user interface. Once you have received the right credentials, which consist of an account and of course your grid certificate, you are set to go. First you need to divide your problems into smaller units called jobs. We've spoken about this before during the PBS tutorial. These jobs are units of computation and can be submitted to the grid. The way to do this is to describe each job in terms of a job description language, which is called a JDL file. This is not a programming language but consists of attributes which describe your job. In the JDL description you describe amongst other things basically the executable to run and its parameters, the files that need to be moved to the grid node on which the job will run, so basically your input files, and any requirement on the environment that you're going to run on and on of course the worker node, so stuff like the amount of memory, the number of cores, available disk space and so on. And this is also the kind of stuff that you can specify in your PBS files as we've seen earlier. Each job in the form of the GDL file is then submitted to the workload management system, and the GLI WMS, so the workload management system, will actually distribute that job to the different clusters. So these clusters consist of several machines, the compute element, which is the information broker or the job broker for the entire process, which communicates with the worker nodes to set out the different jobs. And the worker nodes actually are the servers that do all the work. When finished with a job, these will report back to the CE, so the computing element, which in turn will inform the users about the status of the job. So next we show an animation with a general view of grid functionality. Here we have the same situation as before with 4 clusters and 2 users that submit jobs, but now we use decentralized workload management system to distribute the jobs for us. So what you can see is that the jobs are first being queued to the WMS and that they are then distributed across the 4 clusters. And this causes the jobs to be much more equally distributed across the 4 identical clusters, as you can see. But the properties that we just talked about give you certain grasp on what your application needs to look like to be able to use the grid to do large-scale computation. And grid computing is a form of distributed computing which can be very powerful when applied the right way, but which does demand certain characteristics of the job. So the grid is best suited for application with a data parallel nature that require many simultaneous independent calculations. This means that the job can be split up relatively easily in multiple independent parts. And this is what is known as an embarrassingly parallel problem, what we also discussed during the cluster computing part of this course. So it becomes interesting when submitting hundreds or thousands of jobs simultaneously. A single grid job is slow because the overhead due to the scheduling and bookkeeping of the job status. So job submission has a high overhead. Submitting a Hello World program can take minutes. Therefore, compute-intensive applications and simulations that need to run in parallel for a large number of scenarios are best cases to be deployed on the various nodes on the grid. So a good example is the BLAST application, where you can do many thousands of runs and you really can scale across an entire grid of resources. So to talk about some best practices. For one, users have to do a lot of things themselves. That's really something to keep in mind when using the grid. You are submitting your jobs into unknown territory. For this reason, programs, data and other requirements should be specified, and the program should be described or scripted portably and without any hard-coded paths. When users submit a bunch of jobs, you need to compile and package the application like you would for any other system. Get the data and software to the nodes. This can also mean that you first need to stage your data to a particular cluster to be able to use it over there, because the network connections to other storage sites might be too slow. And of course, deploy the applications and replicate all the databases. Then you have to submit the job and monitor all the status of all your jobs. Fault tolerance and error handling are not easy on the grid. Users keep an account of their jobs and check whether they are completed successfully. They need to embed logging steps in the scripts for debugging. However, there are tools to help you deal with failures and resubmissions, and we'll talk about these, for example, in the Pilot Job Framework slides. So you need to adapt your problem and design your implementation considering memory, wall clock times and availability of scratch space. And our advice therefore is to start small and then scale up gradually. You need to learn how to overcome the problems associated with grid computing. So keep in mind that things will fail, but grid can be worthwhile for several large-scale applications.